Hi everyone, welcome back to the YouTube channel. This is lecture 5 of our Precast Concrete Lifting course. In this lecture, it's all about worked examples. We're going to take the wall that we would have seen previously. So it's a wall with openings. Here we can see it being lifted vertically, but let's imagine that wall was cast on its face and that we had to demold it and then tilt it and lift it like this. So I'm going to let you over to Matt and he's going to describe exactly how to do that. Thanks everybody. Don't forget to like and subscribe.
So this is the second last module that we have here in the precast lifting course, and it's we've covered all the technical aspects up to now, and we're not going to introduce, I suppose, any more technical stuff now. It's just the next lectures today and next Wednesday are to basically reinforce what we've covered already, try move by means of worked examples this week, and then next week to give kind of guidance on the best approach to doing your own calculations, and the best approach is to kind of develop your own spreadsheet, nice, clear, consistent, etc. Depending on the type of lifting problem you're working with, sometimes the calculations can get that bit longer and you're writing out the formulas every time, etc. So having a spreadsheet to assist you in carrying out your designs can be quite helpful. So before we start, we have this admin slide. I mean, you know the deal at this stage. So we'll have the questions at the end, all microphones off, and we'll have the handout sent out afterwards. And any technical questions, my email is there. So this course, as I said, it's the second last one, work examples, and next week's one will be based on spreadsheet preparation. As always, we'll have a quick recap of what we discussed last week, and then we're only going to manage to fit in one worked example in this session because it is quite long. It's a wall panel, tilting, lifting, so demolding, tilting, lifting, etc. So there's a number of different reiterations of the calculations to be carried out, and it's an example that I picked that's not going to work out the first time. So it's all well and good when your design works out the first time, but this is kind of specifically kind of designed so that we have to go back and review some of the inputs, etc., to figure out what the best solution is. And there's always different ways of doing it, so I selected a couple of different solutions in order to develop a suitable design. So firstly, from last week, we discussed lifting using rebar and strand, and we come up with a different number of formulas for that. It's essentially a different approach than what you take with lifting pins or wavy tail sockets. The analysis is different. So you're basically checking in terms of the steel checks. You're primarily in tension, and you're just checking the cross-sectional area of the lifting loop. And in terms of the concrete checks, you're generally checking the anchorage. I just noticed a typo on my slide here. I'll have this corrected before we issue these out. So this is not concrete pry-out failure. This should actually say wire loops. So essentially, when we lift with rebar or smooth bar, we have this formula here for the steel strength up on top. Essentially, what you have is two legs, the strength of the bar, and the area of steel, two legs. And we had this K1 factor, which essentially just represented a reduction factor, got to do with the bend diameter of the the loop in relation to the hook, etc. So there's some reduction factors there. And that was your steel check. Your concrete check then was essentially a anchorage check formula, and I had a couple of slides on how this formula was derived, and it had certain assumptions within it. But it all stems from chapter 8 of Eurocode 2, how to calculate the anchorage length of a bar. And that's it. And also, when you calculate the anchorage length, your strength still must be less than or equal to the actual strength of the bar. So you don't gain anything from adding more than what's required in terms of the anchorage length. When we went on to pre-stressing strand, we had similar formula again, except we had the introduction of this K2 factor. And this K2 factor was there to represent if you're bundling bars together. There's a reduction. You don't get the full capacity of all bundled strands. And similarly, then we had, as I said, this is supposed to be wire loops. I'll correct that. K1 times 2 times FYD, and this is the breaking strength of the wire loop. You know, it's not something that you can calculate too easily. It's something that just has to come from the manufacturer, come from test values. This breaking strength, and you got 2 legs, and you got the K1 factor, which is the same as the K1 factor through them all. Down here on the bottom right, we just had these 2 little diagrams for the angle that you would encounter when you're lifting. So there's kind of a change to the distribution of force in the lifting loop, rebar, or strand that needs to be accounted for. So that was kind of what we did last week. So now moving on to a worked example that we have here. So essentially, this is a wall panel for an industrial facility. So it has got large openings in it to allow M&E services to go through. It's 4 meters long, 1.5 meters high, and a number of 500 by 500 openings. And essentially, what we're doing here is we're casting it on the flat in the factory. It's going to be demolded in the factory, put into storage, transported to site on the flat, tilted up into an upright position on site, and then lifted finally into its final location. So a couple of the parameters that we set in order to do this. In the factory, we're saying that we're demolding on the face using a gantry crane. We're transporting on and off the truck using a mobile crane, tilt into an upright position using the mobile crane, and lift and install using the mobile crane. So the same crane being used on site. And in all cases, we're assuming that the number of effective lifters is 2. Makes it easier in the factory. All the chains go back to the one hook, but as a result of that, you have to, only 2 of them could be assumed effective. We're going to use spherical head pins for the demolding in the face. And then when we get to the tilting and lifting, we're going to use wavy tail sockets. In the factory at the mold time, the concrete has achieved a strength of C2025, and on site, when we're tilting and lifting, the concrete strength is C4050. So they're the kind of parameters that we set out for this problem. We're going to introduce a couple of more parameters as we go through it, but we'll do that on a case-by-case basis. So first place to start is obviously the demolding. So start as you would in terms of the whole process. Start with your demolding requirements first, then move on towards your tilting and lifting. So we've covered, as said, through lectures 1, 2, and 3, everything that you need to know from the technical side for this particular worked example. So we're going to implement those now. 4 lifters, and I suppose logic dictates that you want as much concrete around the lifter as possible. You want the lift load balanced as much as possible. I mean, this is convenient in a way that it is symmetrical. So often you're going to have units that are not symmetrical. They're going to be top heavier on one side and the other, etc. So you always just need to know where your center of gravity is and kind of focus your lifters uniformly around that center of gravity, or else make allowances for where you have the lifters placed. So first step, calculate the weight of the unit. Unit weight of concrete, 25 kilonewtons per meter cubed. Volume of the unit, 4 meters, 1.5 meters, 300 millimeters thick. For now, and just to be that little bit on the conservative side, we're not accounting for the openings. So we're just taking it as one solid slab in terms of calculating the weight. We will account for the openings when we're calculating the capacities, but as the demand is a function of the weight, if we're slightly heavier than what it actually is, we're on the conservative side. So we're just taking it as rectangular object, 4 meters, 1.5 times 0.3, work out your volume, and then you work out your unit weight from that then. So 45 kilonewtons, 4.5 tons is what this particular unit is. So in order to get the demands on the lifters, there's a couple of other parameters that we need to look into. So the type of formwork, again, this is a oil steel mold. The side stripped, so the only contact for demolding is going to be the base. So the adhesion factor is 1 kilonewton per meter squared, and we had a table for that back in lecture 1 for the different options. And the contact area is, as I said, the base, so it's 4 meters by 1.5, so that's 6 square meters. Dynamic lifting coefficient. The worked example is for demolding in the factory at this stage, and it's assumed a gantry crane is used to demold and transport onto the bed of the truck. Thus, the dynamic load coefficient is 1.2. And again, refer back to lecture 1 for the table on that. Further on in this worked example, we're going to have a dynamic lifting coefficient of 1.4 to account for the mobile crane that's going to be used on site to unload the truck, tilt and lift. So we have to calculate those numbers as well for that additional dynamic lifting coefficient. Number of effective lifters, as I said at the start, we're taking all 4 lifting chains back to the 1 crane hook. So only 2 lifters are assumed effective, and thus each lifter needs to be designed to take 50% of the total load. And the chain angle, we're typically, chain angle is given as 30 degrees. So we're not going to exceed 30 degrees. So we'll use that as our limiting factor. So our first demand check is the mold for demanding. So the force required to break the adhesion of the mold. And that's the formula here. It's a function of the weight of the unit, the adhesion factor, the area, and then your partial factors for load and the number of effective lifters. So the only additional thing here is your partial factor for the load, 1.2. Typically, Eurocode states that's 1.35, but we have shown in lecture 1, due to the reliability and the certainty around the value of our dead load, that we can reduce that to 1.2. And we get a value of 30.6 for that kilonewtons. You'll often find that this particular scenario where you have a flat surface and sides are stripped, etc., that this is not going to govern, and no different here. So when we look at the second demand check that we need to do, which is for lifting. So once the adhesion is broken, we need to lift out of the mold, and that basically introduces the dynamic lifting coefficient. So as I said, we have 1.2 in the factory. It's a more controlled environment. We're using a gantry crane. On site then we're using a mobile crane, which is going to be 1.4. So we're calculating both of them here. So we're calculating all our demands now, and we'll carry them forward as we need to when we're calculating the capacities and cross-checking. So we calculate the formulas here. Dynamic coefficient times your weight of the unit times your partial factor divided by the number of effective lifters. And you can see in the factory, we end up with 32.4 kilonewtons per lifter. And obviously when we get to site then, because of the higher dynamic lifting coefficient, we've got 37.8 kilonewtons. So for simplicity, and because we're going to be using these spherical head lifters to lift off the truck on site, we're going to just carry forward this number here for now. So it's the worst case that those spherical head lifters are going to experience, and we're going to carry that forward, just to simplify it a little bit anyway, and we'll see if it will work with those conservative assumptions. If it doesn't work, we can come back and refine our result. So taking those values, that 37.8, we need to perform a bit of trigonometry in order to determine the actual tension and shear load on the anchor. Because I said we're lifting at an angle of 30 degrees to the vertical, so a little bit of trigonometry there, and we come up with these results here. So 43.6 in the chain, 37.8 in tension, 21.8 in shear. So that's what we're going to use to calculate the or cross-check against the capacities. From that, our maximum load is essentially just over 4 ton. So we want to be selecting a lifter that's greater than that. And so we're selecting here a 5 ton by 240 lifting pin. The wall panel is 300 millimeters thick, without, I suppose, too large cover requirements. And with the former, the domed recessed former, the lifter is going to be, actually on the next slide, the lifter is going to be 10-15 millimeters below the surface. So 15 millimeters in this case. 240 plus 15 is 255, which leaves us 45 mil cover on the back face. And I think the requirement for this was 30 mil cover for this job. So we had that satisfied. So we can carry that forward and calculate all our calculations based on that. Some of the other parameters we need to pull off using that lifting pin are the pin diameter and the foot diameter. So you just pull those off your tables and you'll use them when you're carrying out your capacity checks. So that's all we needed for demand. And we're going to carry these formulas throughout all of our capacity checks now. We won't. So when we look at the tension capacity, we need to consider concrete cone failure, concrete pull-out failure, concrete blowout failure, and concrete splitting failure. So we're not covering the steel checks here. We've kind of covered them previously and shown that your typical brochure values are satisfactory in terms of bringing it from the global safety factor to the limit state design in the Eurocode. So once we have satisfied that your 43.6 kilonewtons is less than your 4.36 ton is going to be less than your lifting pin here, that satisfies those checks. So we're focusing mainly on the concrete because there's a bit more to it. In this particular aspect of demolding using those pinhead lifters, we don't need to consider concrete blowout failure. It can be ignored since the edge distance, which as you see on the diagram here, our edge distance, we've placed it in the center here of this kind of square area. And so it's 250 from the edge. And so our edge distance of 250 is not less than half the embedment. Half our embedment is 255 over 2, which is 128. So we don't need to consider blowout. Generally don't when you're lifting like this, but when you have wall panels and such, and you'll see when we're doing the lifting checks later on site, that we will have to consider blowout. Concrete strength, C2025, your partial factors for your concrete, your lifting and handling for concrete and steel, your material strength of the I suppose rebar, and your partial factor on rebar if we need to account for any rebar, additional rebar. So plugging through it, we pull up the formulas that we had from the lecture 2, which was all about tension. And this is the formula here. In order to get our design capacity, we get a characteristic capacity, area factors, as well as a number of few other factors divided by your partial factors, safety. And it's all a function mainly of the effective depth, which we have is 255. We need to understand how much concrete area is available to us. So in the blue outline here is the critical area. So the area that if you have more than, you do not need to consider any area reduction factor. In this particular example, I've highlighted the green area. So it's a kind of a rectangular area there. We could say we have a little bit here as well, but again, because of these kind of re-entering corners and all that, stay on the safe side and see where your calculations lead you to. Calculate your critical edge distance and you work out your area formulas. So you can see clearly here that the green area is less than the blue area. And when we work out the numbers, it's actually 65%. So 0.65 is our reduction factor on the concrete cone area, the breakout body. So we'll hold on to that and it'll be plugged in here now in a few minutes. We need to calculate the characteristic capacity, and that's a function of the cube strength and the effective depth. So we can just pump in our formulas here. and this KN factor, which is recommended, is 11.9 from the CN 15728 code that we introduced back on day one. Bring in your formulas, and you're here 242 kilonewtons. Oh, great, loads capacity. Well, we just got to account for the rest of the reduction factors first. Because we are close to the edge, we have not reached our critical edge distance. So we have reductions. So as well as an area reduction, we have an edge reduction, and it's a function of the actual edge distance divided by the critical edge distance. So again, we pump into our formulas here, and we get a 0.89 factor there. These other factors, they're not that critical in this particular case, so they're just kept as 1. So when we bring all our formulas together, bring all our parameters together, and the partial factor for concrete and partial lifting handling factor, we go from 242 kilonewtons down to 62 kilonewtons for that instance. So we'll hold on to that 62 kilonewtons for now, and we'll bring it all together at the end in the summary table. Pull-out failure, again, it's required to be checked, but not that critical for these particular types of checks, particularly when you have a headed stud, etc. You're more than likely not going to have this as a governing failure. And when you look at the form, it's a function of the diameter of the shaft compared to the diameter of the foot, and the spherical head lifters are designed such that this doesn't govern. So when you pump into this simple formula here, again accounting for your partial factors, you get a value of 110 kilonewtons. So again, that's going to be greater than the 62 we saw on the previous slide, so we don't have to worry about that one too much. If we continue then with concrete splitting failure, again, not that critical in these particular examples. We have quite I suppose a distance, but potential splitting locations are along these kind of short paths here along the 500 mils. We can calculate what we need to completely resist a 5-ton lifter, so 50 kilonewtons, and you only need 103 millimeters squared. So it's kind of a quick check just to make sure that across each interface that you have that steel, and generally you're going to have more than 2B10s across those locations anyway. So it's when you get into the higher loads and thinner panels, it's when splitting kind of becomes more of an issue, or if you're closer to outside corners, etc. So we don't have to worry too much about that. And as I said, the other tension check was concrete blowout, so we don't need to check that now. Concrete edge failure is the first of the shear failures we need to check. So we discussed all the shear failure modes in lecture 3. And when we draw our diagram, it's always good, always draw diagrams. So we said only 2 are effective. So there's only tension in these chains here and slack in the other 2. And we have shear parallel to the edge. And that's kind of what we're going to check here. Where edge distance is 250 and our thickness is 300. So we're going to take those values forward. We have to calculate a similar area of steel, sorry, not area of steel, an area of breakout for the shear edge. And when we do calculate this, our C1 is 250 mil. We calculate 1.5 C1 in both directions, in left, right, and down. And we have the full availability. You can see from the diagram, we can easily get 1.5 times 250 to the left, to the right. But in the thickness, we do get caught a bit. So the thickness, we only have 300. So there is a small reduction there. So a 0.8 factor on that. Again, very similar setup to the formula, except in terms of shear, we've got a characteristic capacity, an area reduction, a bunch of other reduction factors, and our partial safety factors to account for. Similar functions. I'm not going to go through them all because I'm conscious of the time. But essentially, when you crunch through all your numbers there, you end up with a value of 78.3 kilonewtons. So again, the black is essentially the formulas, and the blue is essentially the workings of those formulas out. So you should be able to track these worked examples quite easily. A few other workings to basically calculate all your partial factors, and the only thing here is that the angle factor is 2 in this case, because we are parallel to the edge. We're not pulling directly against the edge, we're pulling parallel to the edge. So we have a slaving there, so we have a factor of 2. And when you pull all your factors together, you end up with a design resistance of 55 kilonewtons. Local concrete crushing is the next one and often governs, and it's a function of the diameter of the bar, as well as the concrete strength and the strength of the steel. So in the pumping that in, so 18.52 is our capacity there, and basically, it's considerably less than the edge distance failure. So that's probably the one that's going to govern. And the final shear check is concrete pry-out failure. And it's a function of the concrete cone failure in tension. So we calculated that previously, we bring it forward, and we work through this simple formula again. And because we're considerably have a considerable depth into the unit, we're greater than 60 millimeters, so we have another factor that we can avail of there of 2. So again, 215 is your pry-out. So we start to bring everything together, and we can work through, because we have tension and shear acting at the same time, we can calculate our interaction checks. So it's demand over capacity in tension squared plus demand over capacity in shear squared for your steel check. You get a value of 1.33, which is less than, it's greater than 1, so that's not acceptable. And the same when we look at the concrete checks. So I'll skip forward to the next slide. And as I said, like, the purpose of this is that it's not going to work out first time. So we need to come up with a solution to make it work better. So we need all our utilizations less than 100%. You can see that for the steel checks, that the individual ones, the tension and shear, work out, but the interaction doesn't. We do have an issue with the individual shear check in the concrete. And obviously, if that doesn't work, the interaction check isn't going to work either. So you can see here the 3 areas highlighted in yellow where we need to address. So there are a number of options. And depending on what's most practical, really. So in the factory, you could say that you're going to use a spreader beam, engage all 4 lifters, and then therefore all these demands will divide by 2, and that will get you over the line. Spreader beam is not always practical. Another option that we're going to do is we're going to increase the lifter. So if we look at what is the governing failure, so obviously we got failures of the steel here, and it's not working. So if we increase the size of the steel component, that'll help. The governing failure here is the local crushing. And if you're to look at the formula for that, the 3 factors are strength of the steel, strength of the concrete, and the diameter of the lifter. So by increasing the size of the lifter, we increase the diameter. So by doing all that, this is the revised summary table that you're going to get. So you have now satisfied the steel checks by going to a 7.5 ton by 240 lifter. In terms of your concrete checks, you've increased the local crushing capacity, and you have now satisfied the shear check, but you still have an issue with the interaction check. So that's still not working out for us. So if you recall back to the start, I said we took a kind of a conservative approach to the calculation of the weight. We hadn't accounted for the 500 by 500 openings. So if we were to account for those 500 by 500 openings, take them out of the weight of the unit because it is an opening, and we end up with a summary table like this, or our demand reduces in that fact. And then our final one that we need to check was our interaction, so we're at 92%. So that works. So that's the kind of process that you go through. Can you refine the weight? Can you increase the concrete strength? Can you add more lifters? Can you add a spreader beam? There's a lot of different factors, and some of them, depending on what the unit is, depending on your program, some are more beneficial than others. I mean, you don't want to be increasing the concrete strength in the factory because it's going to have to stay in the mold longer, etc. So some of them are more beneficial than others. So when we get to the site, we are taking the unit off the truck, putting it down the ground, maybe on a bed of sand or something, and tilting it up. So when you're doing that, the assumption is always that we've got one edge bearing on the ground. So when we're tilting, we're essentially putting a 100% of a shear force through the lifter through that edge. One end here on the left is bearing on the ground, and our weight of unit is acting through the center. So you can work out what the value of the shear force is, and basically take that as your design. So I think there's probably an overly conservative value here, because the ground is taking some of the weight as well. So we'll just continue on that basis because that's what's done. So once we've worked out our value, 32.4 kilonewtons, this is kind of how the breakout body is going to happen in terms of the shear. And we select an anchor based on that 32.4 kilonewtons. So we need it to be working in shear. So like we would have shown again in lecture 1, the steel checks, that your shear capacity is generally going to be half the tensile capacity, and we showed formulas to prove that. So if you need 32.4 kilonewtons in shear, well then it's an 80 kilonewton lifter, so that'll have 40 kilonewtons capacity in shear. And again, just pull off your extra values that you need, such as the length, the diameter, etc., because we'll need those for the checks. So because this is only a shear failure, or loaded in shear when you're tilting, that we're only going to look at the shear checks here, and the main one being the concrete edge failure. We're quite close to the edge now. We're 150 millimeters to the edge with a large force on it, and we're going to have a to check again the same parameters. In this case, we're C1 is 150, so 1.5 times C1 is 225. So we have essentially 225 available to the left, available to the right, and available down the panel. So we have those distances available, and therefore we don't actually have an area reduction factor. When we calculate all our numbers again, we get a characteristic capacity of 63.7, but all our other factors as well, calculate them there. They're all coming in as 1. This time now, we cannot avail of, I suppose, any gain from the angle factor, because we're pulling directly towards an edge now. So that has to be equal to 1. So previously we had it equal to 2 because we're parallel to the edge. This time we're perpendicular to the edge. We're pulling right against the edge. So that becomes 1. So we pump all those in, and all our factors ended up being 1. But because it has been, I suppose, quite close to the edge at the starting point, we end up with a design capacity of 28.3 once we account for our partial factors. So again, we'll hold on to that, and we'll bring that forward with us. When we look at the concrete crushing, when we bring forward, so the diameter of the rebar in this was 28 millimeters. We're now, because we're on site, we actually have a higher strength of concrete, so we can put in 40 in here. So, and when we pump all those numbers, we can get a value of 51.4. So it's almost a reverse of what we experienced when we were demolding. So demolding, we had quite a low value for the concrete crushing resistance and a higher value for the edge failure, but it's the reverse here. So you're not going to have the same failure mode governing every time, because it's very application dependent, very geometry and edge distance dependent. So that's kind of one thing to note there. And then pry-out failure, again, it's a function of the concrete cone, and we're not looking at tension failure modes here, but we have to calculate that anyway. When we're doing the lifting after this tilting check, we will be calculating the concrete cone for this exact location. So that's why I've just put a note in here to see slide 49 for how that concrete cone failure of this location was calculated. This 71.3 value, how that was calculated. So again, nothing else changes from before. We calculate that, and generally pry-out doesn't govern, so it's 142.6 is our value there. So we bring all our numbers together, and we were only dealing with shear failure modes. So that's just the right hand side of this table is all we're concerned with. The capacity is 40 and demand is 32.4. So we got 81% utilization. Because we're only dealing with shear failure modes, we don't have an interaction check to check. And then when we look at the concrete failure modes, we can see that the governing one in this particular case is 28.3 kilonewtons, which is concrete edge distance. And that's less than our demand, and therefore we have to come up with a solution. When we are tilting, you're generally always going to be putting in additional reinforcement. It's kind of, I suppose, recognized, and this kind of calculation proves it, that it's very difficult for wall panels to get it to work with just the concrete alone. So you're always going to add in some degree of additional reinforcement. And we spoke about this at the end of lecture 3, different options available and what they mean. The formula is relatively straightforward. It's the number of legs available to you, the area of steel, the design strength of steel, and this K10 factor, which is the efficiency factor. So if you have a one like this diagram here in the middle, where you've got a strut and tie approach, your efficiency factor is 1, but either of the top or bottom diagrams, your efficiency factor is going to be 0.5, given that because it's hard against the lifter, but you can't necessarily guarantee once the concrete's poured if there's a little air pocket against it or not. So there might be some potential for movement. And generally, with a design like this, you double up your shear, your tilting reinforcement like this, because often, depending on how the unit is handled, you're not necessarily guaranteed to know which face is up on the truck. Often you might have to tilt it in the factory to get a look at the other face for touching up, or if there's other additional works to be done. And therefore, when they tilt it back down, there's no guarantee to tilt it back down the same way. So depending on how you're lifting, you kind of have to account for both faces being face up, and then you're covered in terms of your design. But only one of these is effective at any one time. So for formula there, what we've suggested to put in was, for this particular example, was a B16 cranked U-bar like this. So it's 300 millimeters thick panel. So it wraps around your lifter and then bends back down your panel. So that's B16, has an area of 201, the efficiency factor of 0.5, crunch through your numbers there, and you get 48.5 kilonewtons resistance. This is just a slide to represent the efficiency factor. So if you're using the strut and tie approach, you can use K10 is equal to 1. If not, 0.5. So start with 0.5 and then you can refine afterwards. And here, this item here is your typical cranked rebar solution for a single case. So you just mirror that to account for both sides. When you do that, you revise your table, summary table. So what has happened is our concrete edge failure has changed now. So we're not relying on the concrete anymore. We've supplementary steel in there to do that, and we compare that against our demand. We now have 67% utilization. So that checks. And then the last aspect is lifting of the wall panel. So the wall panel is now in an upright position, ready to be lifted off the ground. So in this particular case, we're only talking about tension, but due to the fact that we're going back to a single chain hook, we're going to have some shear to account for as well. So again, conscious of time, so apologies for flying through this, but you will have all the slides afterwards to go through it again in your own time. So these are the demands that we calculated before, back at the start of the lecture. And sorry, we actually had to recalculate them because we're using a socket, and sockets are generally confined to 12.5 degrees lift. So that's what we're using here. So what we end up doing then is we still have the same tension force to contend with, but the shear force due to the smaller angle is a lot less. So we've got 37.8 kilonewtons in tension and only 8.4 kilonewtons in shear. And the shear, when we get to it, it's parallel to the edge again. So again, we're going to gain from that. Tension capacities, the only thing that changes in terms of the input parameters is the concrete strength. So we're now on site and we have C4050 on site. So we have to look at the depth of the anchor into the concrete and what kind of concrete cone would develop. So into the page, we only have 300 millimeters of thickness, so we're going to be confined by that anyway. And the depth, so this particular bar was 632 millimeters, and that's what we use in the design. The representative kind of breakout is here, bit, close to the edge here, and what happens if you are, I suppose, too close to that. But for the sake of argument for this, we're saying that we can avail of all this full blue line here. So crunching our numbers, we end up getting a massive area reduction because we are only 300 millimeters thickness, and it's a function of the depth, 1.5 times the effective depth. So the area required for no reduction is quite large. It's you're talking about a meter nearly on all sides, and when you crunch that, you get only 16% available. But to counterbalance that, to make the calculation look some bit more reasonable, is your characteristic capacity. Because you are so deep into the concrete, your characteristic capacity is on the high end as well. So they kind of counteract each other. You're gaining by going deeper, but by going deeper as well, you're also getting larger reduction factors. So a couple of more reduction factors there got to do with the gauge, 0.75, and we end up getting a design capacity of 71.3. So we'll carry that one forward. Pull-out failure, not going to go through it. We got 164 kilonewtons. We'll bring that one forward. Now, blowout. Haven't spoke about blowout yet, but because we're in I suppose, a relatively thin wall panel, we're only 150 millimeters towards the edge. So what can actually happen is that you get a blowout emanating from the foot of the lifter. Now, it is a socket we're using here. It's a wavy tail socket, so the distribution will be that bit more favorable. But again, just to stay on the side, we assume that all the pressure goes through a single point, like would be the case with a spherical head. And this is the kind of breakout body that gets derived according to the code. And we have the formulas here, but a very similar setup: characteristic capacity, area reduction, some other factors divided by your partial safety factors. So we can crunch all those numbers, and we just need to check, do we have enough area? So our breakout body, so our edge distance is 150. So we need to be essentially 300 in all directions. So we need a square 600 by 600. But we don't have that because we're down into this 500 wide column portion. So we have a small bit of reduction shown here by the green hatch, and it ends up, when you work it out, to be 0.83. So a bit of reduction there in the area. Other factor to calculate is the edge distance. We're close to the edge in terms of this C2 value. We're not close to the edge of the panel, but we're kind of close to an internal edge, if we want to call it that. So our edge distance into the page where the lifter was 150. So, and this edge distance here is 250 then. So that's what we're just calculating here. Small reduction, because again, that can break out at that point. It has no resistance once it gets to that edge. So 0.95. Pump in all your numbers here, and you end up with a value, a design value of 102 kilonewtons. And in the last tension failure mode was the splitting check. Again, we're using a slightly larger lifter, 80 kilonewtons for the full capacity. We need 166 millimeters squared. So 2B12s will kind of cover that. So you're generally always going to cover that for these kind of larger areas of concrete. Really quickly then is the shear failure. Similar to how we calculated it the first time for demolding, we're parallel to the edge. So your breakout could be this guy here. Working through the formulas, we don't have an area reduction factor in this case because we're able to generate the full breakout body. and calculate all these parameters. You get 63.7, that's your characteristic capacity. You get the angle factor here, which is 2. And then you get to use this guy here because we're parallel to the edge. You get 56.6 as your design capacity. Calculate your local concrete crushing, which works out to be 51.4. And then your pry out. So this is the value that we used, I suppose, previously as well, for the tilting check. So 71.3 kilonewtons. I'll skip this slide and I'll just jump straight to the table. So when you bring all your numbers together then, so because we were lifting, we had tension forces and we had shear forces. So we got to check both and we got to check our interaction. So by doing that, you can see that it all works out. So the lifting on site wasn't the most governing of cases. It was more tilting and demolding that kind of would govern this design. So we gained on the concrete strength and also the position and depth of the lifters as well. So the final slide that I have is just some general tips just to finish it out. So I suppose when you're doing lift and design, you should always be conscious of where you're putting the lifters. And generally, but not always, the demands on the unit itself are going to be less when you're lifting than in its permanent state. But often an example is for a lift shaft, where you could have 3 shafts and a cover slab on top. So if the lift shaft was 9 meters, 3 meters each shaft, your slab in the permanent case is only spanning 3 meters. But during lifting, it's a single unit, and your lifters are just in from the edge, so you could be spanning 5-6 meters in the lifting case. And also another example would be pitching walls and pitching columns. When you're tilting those up, they haven't been designed in the permanent case for that effect, particularly if you're pitching around the shallower axis, the thin section, like with this example here. So just bear that in mind, and make sure that's kind of looked after. And then the last thing is just a general rule of thumb that we use is when we're kind of lifting reinforced concrete units, that we use L/5 in from the edge, and for pre-stressed units it's L/10. So L being the span of the unit over 10, span of the unit over 5. And if you're to work out your forces, your bending moment diagrams, what that does is it kind of keeps it more balanced, particularly for like a rectangular section for a beam, reinforced beam. Your bending moments, your hogging and your sagging bending moments will be almost balanced. So you're trying to just not put too much force on it in that case. So ran a little bit over, but not too bad. So that kind of covers the worked example. I knew it was going to be long, so I knew we'd only fit one in, and we just barely fitted one in. So there's quite a lot in it, but I think it was good to get an example right through from start to finish of something that you're going to be dealing with quite a lot at a time. So demolding, pitching, and lifting in kind of a flat panel format for demolding, and kind of a thin panel format for tilting and lifting. So if anyone has any questions, feel free to ask. So that kind of concludes this lecture.